Welcome to The Explainer. Today we are diving straight into the hidden rules that literally keep our entire digital world from collapsing. You know, every single time you snap a photo, stream a track, or watch a show, there are these invisible mechanics working frantically behind the scenes to make the whole shebang happen. So let's pull back the curtain and uncover exactly what they are. Think about this massive number for a second. 150 megabytes. That is roughly the amount of data required for just one single second of uncompressed, high-definition video. I mean, if you're binge-watching your favorite show, that translates to gigabytes of data flooding through the network every minute. And because of that massive data footprint, the reality is pretty stark. Without compression, the internet as it currently exists would simply be impossible. Without this hidden, continuous intervention, your shiny new smartphone, even with 256 gigs of storage, would fill up completely with fewer than 500 uncompressed photos. And video streaming? Yeah, that would saturate and crash every major network backbone in a matter of seconds. So here's our itinerary for the digital mysteries we'll be unpacking today. First, the data overload problem. Second, how data compression works. Third, lossless versus lossy methods. Fourth, the hidden layer known as metadata. And finally, we'll look at a real-world data workflow.
All right, let's jump right in with Section 1, the data overload problem, and the fundamental concept of Shannon's entropy floor.
Which brings us directly to our hero in Section 2, how data compression works.
Well, how does it work? It exploits the fact that real-world data contains massive redundancy. We're talking about patterns that repeat over and over, which can be cleanly removed. Our ultimate metric for success here is the compression ratio, which is simply the ratio of the original uncompressed file size down to the compressed file size. So a 4-to-1 ratio means your new file is just a quarter of the original size. Typical lossless compression usually hits ratios somewhere between 1.5-to-1 and 4-to-1. But lossy compression, that can aggressively push ratios all the way to 10-to-1 or even 20-to-1.
So what's the difference? Let's break it down in Section 3, lossless versus lossy methods.
Think of these two methods like two completely different personalities, the perfectionist archivist versus the perceptual illusionist. With lossless compression, our archivist guarantees an exact mathematical reconstruction of the original byte sequence. It is mathematically identical, period. Lossy compression, on the other hand, achieves those massive ratios by permanently discarding information. It basically calculates what human senses won't notice anyway and just throws it away forever. Let's look at how lossless compression elegantly groups data using something called run length encoding, or RLE. Imagine a row of pixels in an image, and it goes white, 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 black, black, white, white. Instead of clumsily storing 9 individual values, the algorithm just says, okay, we've got 5 white, 2 black, and 2 white. You've just grouped 9 pieces of data into 3. It brilliantly removes the redundancy without losing a single pixel of fidelity. Now, let's talk about our perceptual illusionists. Lossy compression. This method literally tricks our senses. For photos, the JPEG format uses a discrete cosine transform to aggressively quantize high-frequency coefficients. Actually, scratch the technical jargon. It basically means it targets fine spatial details that our eyes just can't see and dumps them. For audio, MP3s use psychoacoustic models to throw out sounds we simply can't hear, like quiet frequencies masked by louder, simultaneous sounds. If we can't perceive it, the algorithm permanently deletes it to save space. To help organize this alphabet soup of file extensions, let's look at some everyday formats. In the lossless corner, you have PNG for exact, crisp images, ZIP for archiving folders, and FLAC for pristine audio masters. Over in the lossy corner, we rely on JPEG for standard photography, MP3 for streaming audio, and MP4 for streaming video.
Now let's pivot a bit to Section 4. The hidden layer, also known as metadata.
You see, compression is really only half the story. There's a whole secondary, invisible layer of information traveling alongside your files called metadata. By definition, it's structured information that describes or contextualizes a file without actually being part of the primary content itself. But simply, it's data about data. And this invisible layer is absolutely crucial. It's exactly how search engines index the web, how media players catalog your favorite albums, and how your operating system instantly sorts thousands of files. To really see this in practice, just take a standard smartphone photo. Invisibly stored within that JPEG's header is EXF data. This records highly specific details, like the exact camera model you used, the exposure settings, the timestamp, and get this, even the exact GPS coordinates.
Your MP3s have ID3 tags telling your media player the artist and track title, and your PDFs hold document properties like creation dates and software history.
Now think about what that means for a second, because this carries immediate privacy implications. Sharing a photo without stripping its EXIF data reveals the exact location where it was taken. If you share a raw smartphone photo directly to a public website, that embedded GPS metadata travels right along with it, and anyone can access it. While most major social networks do automatically strip this data upon upload to protect you, the raw file on your device retains it perfectly intact.
All right, let's bring all these concepts together in Section 5, a real-world data workflow.
Let's follow the digital footprint of a professional photographer to see how deliberate choices are made at every single stage. Step 1. Raw capture. The camera takes a lossless massive file with full EXIF metadata. Step 2. Editing. The photographer tweaks the photo, but the original stays untouched. Instead, a new XMP sidecar file is added to store the edits as metadata. Step 3. Web export. They export a compressed, lossy JPEG to keep the file small and snappy, intentionally stripping the GPS metadata for privacy. Finally, Step 4. Archival export. They save a lossless TIFF or PNG to keep a pixel-perfect backup, retaining all that original metadata.
So, the core takeaway from this workflow is a golden rule for managing your digital files. Edit in PNG or a lossless format, and export a JPEG only for the final delivery copy. Remember, lossy compression permanently throws away data. Re-encoding a lossy JPEG multiple times is a super common and completely avoidable source of severe image degradation.
Which brings us to a final, provocative question to leave you pondering today. If a graphic designer opens and resaves the exact same JPEG image 10 times in a row, using JPEG compression each time, what happens to the image quality and why? Think about the permanent, cumulative cost of the lossy compression we just uncovered. Every single save throws away just a little bit more perceptual data. These invisible mechanics running our digital world are incredibly powerful, but man, they are unforgiving if you don't know the rules. Thanks for hanging out and learning with me today, and keep exploring those hidden digital mechanics.